In my previous video, nerds75, I made some experiments with bipolar transistors in the common base configuration. And I arrived at a solution like this, and among the transistors I tested, the BF240 was the best one. So I have now added a thermostat for the crystal and this circuitry. To explain what it is, here is a step-up filter, stepping up the impedance from 50 ohms to something much higher. So I can use a much smaller capacitor here to inject a wideband signal into the amplifier. The input impedance on the emitter is in the order of 10 ohms. And the crystal output impedance is in the order of 50 ohms. So I have a severe mismatch, which is required to get a good loaded Q. And then this link gives me the same signal at the center frequency as I have through the crystal. Then the transistor, I have put a resistor here because I want to feed it with a little bit more than 9.5 volts, which is the optimum voltage I found in the previous experiments. And now I will do some measurements on this unit because I want to match it to the crystal filter. The crystal filter has a stray capacitance at this point that I want to cancel with a suitable inductor. And 22 microhenry is probably far too much. These resistors are in order to put a 50 ohm load on this point, 25 ohms in series with 25 ohms, because 50 ohms here and 50 ohms of the signal analyzer in use. And the other way, looking in here, the impedance is 50 ohms, because at this point the impedance is in the kilo ohm range. So I can see almost only this resistor. It is enough to stop VHF oscillations with this small capacitor and this resistor. I don't need a corresponding arrangement on the emitter side. Here is the input impedance and the forward gain. So it's close to 50 ohms into the filter, and the gain is minus 11.5 dB. Those two resistors at the output attenuate by about 6 decibels. So the amplifier itself attenuates by about 6 dB. The design is for an input power level of about 8 dBm. The loaded Q is 1.09 million. Here is the output impedance and the reverse transmission, about minus 70 decibels, and output impedance very close to 50 ohms, 53 ohms at the peak. Here is the forward transmission through the wideband input. At the peak of the crystal filter, the signal level is nearly 2 decibels lower, because some energy goes into the crystal and not all of it will go into the emitter of the transistor. So that means that the noise will be about 2 dB or 1.5 dB larger than it really is when I do measurements on phase noise and AM noise the usual way. I am using my 2-channel direct conversion receiver. You can see the details about this in previous videos of the Nerds series. I have this pulse generator connected now, and I have used it to calibrate Linrod into the system. The two channels have a hybrid in front of them, so I can do correlation measurements with Linrod. I start Linrod here, and I'm running in the correlation spectra mode 1. So you can see the green is correlation spectra, and white we don't see yet. Yes, we do. It's coming up here. And yellow is also coming. It's coinciding with the white. Anyway, what I wanted to show here is it is calibrated, and the spectrum is flat to well within 1 dB. I'm using the same setup as in the previous video, number 75. So it's intended that I will use the interferometer later, but at this time I'm using this signal chain to generate plus 8 dBm into the device under test. But the output is disconnected from here and routed directly to the hybrid that is in front of the two-channel receiver. And there are no stepped attenuators at this time. I want maximum sensitivity. I have set this stepped attenuator to minus 40 decibels. I'm sending the attenuated signal, that's attenuated by 40 dB, to the selective input of the amplifier, and I have adjusted the S-meter calibration so it shows 40 decibels. It says 39.97 or 39.99. And it's hard to get the camera to understand how to manage these very high contrasts, but now it is visible. What I see on the main spectrum is the green trace of a large number of correlation spectra. It is nearly flat. Here I have some leak through of RF interference. And the yellow is the average of 2000 correlation spectra. And it's of course the same flatness. The white, that is the spectra without correlation, and you can see the noise near the center and at the ends. That is the sound card noise, which disappears with the correlation method. I can look at the noise floor, let's say 10 kilohertz up, and it comes here. And I have to wait for it a little bit like that. And it says minus 163 decibels below that 8 dBm reference level. That would be the carrier when this is running as an oscillator. Now I will switch off that oscillator. Well, we have here also 7 dB of correlation advantage, means minus 170 dBc per hertz. And now I switched off that oscillator, so it is much weaker. There is some leak through, but very little. But as you can see, nothing happens to the noise floor. And if I clear the correlation, it ends up to something very similar. So what I see is the noise of the amplifier, and I don't see sideband noise generated by something flicker or so. I have set a bandwidth of about 1 kHz to get faster readings and more accurate. So here is the noise and the correlation advantage. And this is at 15 kHz above the signal. And I will look also 15 kHz below, that's here. I am adding different components from here to ground to try to balance the stray capacitance that comes from the filter, and also these 3 PF to almost ground. Well, it's a fairly high impedance, but compared to infinity, it is something. I have added 47 PF, and now I see 162.4, and the correlation advantage is, where is it? Here. It's only 4.5 dB now, 4.67. With nothing connected, the noise was minus 170.3 on the high frequency side and 170.2 on the low frequency side. But with 47 PF, the noise is about 3.3 decibels higher. So that is a significant loss. And of course, I expect capacitors to cause a loss because the filter should be capacitive. But I am looking at various reactances because the loss will form a parabola and the minimum is going to be the value I want. Here I'm using a narrow filter in the baseband to look at the center of the crystal filter. And here the noise is minus 155.4. And I don't care about correlation advantage. I would have to change parameters significantly to do that, but this is high enough to be a reliable reading. As it turns out, I cannot do much improvement by an inductor. I will plot this to make it more clear. But what I see is that the noise floor is about minus 170 at best, and the crystal is minus 155. So the noise when the crystal is connected is 15 dB above the noise floor, and that is partly thermal noise from the crystal, and it's also that the low impedance gives more gain from the transistor, and what is what I don't really know. I have plotted the sideband noise against the 1 over the reactive impedance. That means against the imaginary current. Minus means capacitive. So here, here, and here. And here, this doesn't look right, it should be lower. And here, and here. So it looks like a nice parabola. This result, that is 22 microhenry. At 10 megahertz, it's a high inductance, and probably the iron used in that little inductor is lossy. A 10 kilo ohm resistor comes here. So the sensitivity against real valued impedances is very high. I will look at the components to see what is the losses. The network analyzer is designed for measurements in 50 ohm systems, but the impedances I'm looking at are much higher in the kilo ohm range. So I have to do measurements another way. I have designed this simple filter, and it looks like this. On the network analyzer I can see Q is 99 and the loss is 44.8 dB at 10.4 megahertz. The value stamped on the capacitor is 15 pF and on the inductor 12 microhenry according to the color code. I have placed a 91 kilo ohm resistor in parallel, and now the Q is a bit lower and the loss a bit higher. 91 kilo ohms causes the Q to drop by almost exactly 6 decibels, and the Q goes down by a factor of 2. This means that the loss resistor parallel to the inductor, the equivalent loss in parallel would be 91 kilo ohms, and that is probably causing noise in this oscillator design. 10 kilo ohms was causing about half a dB. Not very much, but something. And 10 times higher might give 10 times less, means 0.1 dB or so. Not much to worry about, but here maybe 0.3 dB for the bigger inductor. I will continue to look at these things. I can check the capacitor on the network analyzer. Now the connector is open, and what I see here is a very high impedance, and it alternates between capacitance and inductance. And then I connect the capacitor here, like that, and this is what I see. And if I change the frequency, the marker frequency, you can see 15.3 pF, and it goes up now when I am at 125 megahertz, but very little, and the accuracy should be good in this range, so I say 15.5 pF. There are convenient tools on the internet that give me the reactive impedance of the capacitor, 874.5 ohm. Then I feed that impedance into another calculator on the internet, and that gives me the inductance as 13.4 microhenries. Then I can use this site to check what I have found. So I feed the values in here, and I get the results here. Q 103 and impedance 90.4. Very, very close to 91 and Q 99. So everything looks okay so far. The capacitors 47 pF, 18 pF that I was using when testing the noise of the oscillator, they are straightforward, just measured to 51 respectively 18 pF. The inductances I arrive at this way is the effective inductance. particularly obvious for the 22 microhenry inductor that comes out as 47 microhenry. That means that half the inductive current is balanced by the self-capacitance of that component. But what I want to know is the effective inductance. That means the reactive current caused by the component that I am adding. Then, of course, there is also a resistive component. In this case, 125 kilo ohms for the 22 microhenry nominal inductor. Now, the changed values, because I have to plot against the inductive current, that's 1 over the reactive impedance, I get a slightly changed picture. This point has shifted just a little, and this hasn't shifted at all. But here, the 22 microhenry has shifted from here to here. And it has the effect of adding this reactive current, but also that resistance that was 125 kilo ohms. And that could well explain why the values are not a little bit lower. They should be expected to be a little bit lower here. This point has also shifted downwards, but this has shifted very little. Means that I still expect the minimum to be about here. And it is very close to the point without any low inductance. But there is the inductor I already have in the circuit in the emitter of the transistor, and I will check that inductor for inductance and losses. It's this one, an Airwound inductor, and I think it is nominally 22 microhenries. The effective inductance of the inductor I actually used on the emitter is 27 microhenry, 27.6. And if you are observant, you might see there is a small difference in the table here. I made a small mistake that actually doesn't change any of the conclusions. So what I want is something like this point, means 0.6 in 1 over the inductance times 1000. So I will compute what that means. Well, actually very simple. The inductor I have been using had 0.576, so I just need 2 identical ones in parallel, or an effective inductance of 27.6 divided by 2. This means I want resonance in my filter with twice the capacitance, that's 17.6, which means I want to place a capacitor of 15.6 pF in my filter and tune a coil for resonance and high Q. This should be suitable. Resonance with 17.6 pF in total. And it is on 10 megahertz and with a Q of 139. I feed that into the calculator and I have to give it 125 kilo ohms and 14.4 microhenry to get the resonance with 17.6 pF and the correct Q 138 that I observed. 139. Well, so this should be a pretty good choice for the emitter inductor. But the difference I expect to see is in the order of 0.1 or 0.2 dB, not more. One advantage with this new coil is that I could glue it to the box to get a better mechanical stability. The previous coil was a sensitive mechanical resonator, a fairly heavy mass on rather thin wires, so it would have a resonance frequency somewhere close to the carrier and provide sidebands when vibrations hit the table where I have this thing standing. There are other things that I need to modify to reduce mechanical problems, but there are more interesting investigations to do before I decide exactly how to do that. The difference is a little larger than expected. I'm looking here at 15 kilohertz above the frequency, and the correlation advantage is 7.57, and the noise floor, I repeat that, minus 163.22 and 7.54. So the values I found are these ones, and when I plot them in the graph, they come here, and that is a bit below what I expected, and I need to check calibration before really believing this. I did the calibration 2 days ago. I have again injected the reference signal at 8 dBm minus 40 dB, and then check the S-meter graph with the calibration. I didn't change since last time, and it shows 40.02 or something. So the improvement I have seen, even though small, 0.3 dB or so, is real. Here is the phase noise and the amplitude noise that I see with the interferometer. The mouse cross here is on the yellow curve. You can see the color when I move the camera. It's at 3 kilohertz and 142.8 dBc per hertz. Now this is with the interferometer, 30 decibel suppression, actually 29.7, and it's through the wideband input. Of course, I cannot do interferometry through the narrow input of the filter, because then the noise from the Wenzel oscillator will be the dominating noise. So that's a notch on the incoming signal of about 1.5 dB, as you can see earlier in this video. Summing up means I have minus 174.0 dBc per hertz at 3 kilohertz now. At 50 hertz I see 137.4 for the phase noise, and the amplitude noise is up here. 50 hertz is the small peak at 130.6. And summing up for the phase noise, it means minus 168.4. Now that I found the optimum emitter inductor, 14 microhenry as measured at 10 megahertz, I want to look at the output side. Now, since I have only a single transistor, contrary to earlier designs with massive parallel junction FETs, the current here is only 1.68 milliamps. I can try other solutions for the output. The purpose of this circuit is to provide at this point 0.66 volts peak to peak into a 50 ohm load. That is when this is connected here and with the measurement system here. This capacitor and the tuning and the tap controls that. There is another alternative now. This is what I have tried. This is an iron powder core, and it's safe to use it with a very large number of turns on the primary because the current is so low. And then I tuned the number of turns on the primary as well as the number of turns on the secondary and the value of this capacitor to get the same output properties, 0.66 volts peak to peak, and resistive impedance at this point. And I look directly in here with the network analyzer. It is a very high impedance, higher than I can measure with any reasonable accuracy. And here is what I see. The mouse is at 3 kHz and the level is 143.2. So it is a trifle better. I can change the scales like this. And now it's easier to see. At 3 kHz minus 143.3. When I look at 50 Hz here, I should read something like this. And this is 137.8. It seems the iron powder core gives half a dB better performance than the original coil, which had a fairly low inductance and a capacitor across it of about 40 pF in total. Here is what the new coil looks like. It's a lot of turns, I haven't counted them yet. I am now looking through this 330 pF capacitor directly on the BNC connector where I have the network analyzer. And here is transmission through the entire unit with the crystal input. The gain is minus 7.3 dB. And here is the output impedance. It's a small circle, very close to infinity, and I can't read what this actually would mean. It is several kiloohms, maybe. This is the iron core I have been using. It's from Amidon. I want to know the losses of the Airwound core, so I placed it in that filter that I used to measure inductances earlier in this video. And what I see on the network analyzer is this Q187 and the center frequency 10 MHz. I tuned it there. I measured the air cored coil first with the capacitor that gave 10 MHz. I found that capacitance to be 55 pF, including the two 1 pF coupling capacitors. Then I also measured with a much bigger capacitor, 210 pF, including the coupling capacitors, and that gave a frequency and a Q. And then I had checked the toroid, the iron powder core, and with only the coupling capacitors, the resonance was 9.7 MHz, And with 2 additional PF, it went down to 7.89 megahertz. And then I know frequency is proportional to the square root of L over C. So I can compute the stray capacitance of the inductors. The Airwound has a stray capacitance of about 1 PF, so I could neglect that, like I did when doing these kind of things earlier in this video. But for the toroid, as it turns out, the self-capacitance is significant, about 4 PF. So using that capacitance, I can compute the inductance of the coil together with that Q that I found. I find that the loss resistance is 260 kilo ohms, while for the Airwound coil the loss is 53 kilo ohms. Now the uncertainty here is pretty large because of the uncertainty in these capacitor values, but nevertheless it's quite obvious that losses are much lower with the iron powder coil. So I will continue to use that. It's also an advantage from a mechanical point of view. I don't think this iron core is going to be sensitive to mechanical vibrations when I fasten it properly to the box. It is, of course, a little bit sensitive to magnetic fields, but that is not a very big sensitivity for this kind of core. I have removed the secondary winding, 19 turns as it turned out to be, and of course now the capacitance is much smaller. As you can see, the resonance frequency is about 12.8 megahertz. A thin layer of Teflon tape on the primary winding, and then I put back the secondary, 19 turns. And it is wound the same direction as the primary, and both are connected on the ground side, as in the previous measurement, to make this measurement simulate the normal operation. The self-capacitance is a little bit smaller, not much, but the resonance is now 9.48 and it was 9.17 before. With the design as it is right now, only 9.6 volts on the collector and 1.4 here on the emitter means 8.2 from emitter to collector and 1.7 milliamps. This transistor goes nonlinear. Now, whether that affects performance or not is something I have to investigate. Noise is not affected much, but maybe the effective Q, the effective loaded Q of the crystal is changed because the input impedance here might become greater. This is what the unit looks like now, and I have the oscilloscope probe on the emitter to look at the waveform. And here it is, and it is very clearly not a sine wave anymore. It is strongly distorted. I have added this phase modulator directly after the vent cell oscillator that is driving my system now. And I'm using this audio generator to send 5 Hz into that phase modulator. At the moment, I send the signal through 12 dB of attenuation rather than the selective filter. That's just to look at the modulated signal. The 5 Hz sidebands are visible here. Also sidebands at 10 Hz and maybe even 15. Then in the correlation spectrum I see it very clearly. The 5 Hz sideband is at minus 94 dB from the carrier. I now run the signal through the selective amplifier and I see 97.5 dB below the carrier for the 5 Hz FM modulation. So it's a suppression by 3.5 dB. I should expect 3 dB at 5 Hz if the effective Q was 1 million. 10 megahertz means bandwidth 10 Hz at Q 1 million and plus minus 5 Hz. So I should see 3 dB. And I see a little bit more than that. And that is with the waveform you can see here. Now I will attenuate by 6 decibels. And the waveform is close to a sine wave now. And I will reset here and wait for a stable correlation spectrum. It takes some time. What I see now is that the amplitude modulation has become much stronger. It was down here somewhere. That's because I'm not heating the crystal anymore, or I'm heating it 6 decibels less. So the frequency has drifted just a little and I get FM to AM conversion. And I have to tune the frequency to get rid of the AM before I can read the level of the frequency modulation. A very small adjustment, and now I see that the modulation is suppressed by almost 98 dB. So the filter has become a little bit more selective. So there is a degradation because of loss of loaded Q when the amplifier goes into saturation. So I will increase the power in the transistor, and I know from before that that would have a marginal effect on noise and maybe even improve noise a little, because I am on the low side of currents and voltages for optimum performance. I'm feeding the box with 24 volts now, and I have retuned the filter to get away the amplitude modulation. Means I'm centered properly on the filter. The frequency modulation is now at minus 98. So it is a little bit better suppressed, and that is because I have more current in the transistor, so the input impedance on the emitter is a little bit lower, means a slightly higher loaded Q. So, and the waveform I'm seeing, like this, it is closer to a sine wave. The amplitude is a bit smaller. But the gain through the transistor has not changed much. I have increased the power in the transistor significantly, and I now see minus 139 dBc per hertz for the phase noise. at 50 Hertz. 50 Hertz here, and this is the 50 Hertz spur. At 1 kilohertz I have something like minus 142. It's a little bit hard to read it, so I just compress the scale like this, and now I can see easily at 2 kilohertz minus 142. So I have lost a little bit in performance at wide separation, but it is a little bit better at close range. What will be the optimum is hard to say from these measurements as a selective amplifier, but I can change the power in the transistor at a later state when the unit is an oscillator. But I probably cannot decide what is the best at close range, because I don't have the tools to measure below about 5 Hertz. And the improvements are likely to come below that. So maybe someday I have better tools. We will see. Here is amplitude noise together with the phase noise. It is about 4 dB stronger, the amplitude noise at 50 Hertz, but at wider separations above 500 Hertz or so, AM noise and phase noise are the same, about minus 142 dBc per Hertz. So that's the amplifier noise, and it's a little bit higher than it was with less power in the transistor. I want to run the box at 16 volts, as I have the other oscillator for that voltage. So I have changed some resistor values, and I have made them for the power in the transistor to be much higher. So the collector voltage 10.8, and only 470 ohms here gives me 1.6 volts and 3.4 milliamps. So there is now a power of 31 millivolts in the transistor. Here is the waveform on the emitter, 24 millivolts peak to peak. On the output I see 680 millivolts over 50 ohms. A 6.8 ohm resistor from here to ground reduces the output voltage here by a factor of 2. So that means the impedance on the emitter now is 6.8 ohms. With an input signal of 24 millivolts peak to peak, that's 8.5 millivolts RMS, into a 6.8 ohm load, that is 10.6 microwatts, very close to minus 20 dBm. Normally one would expect thermal noise to be at minus 174 dBm per Hertz, so that would be at minus 154 with respect to this carrier, with minus 157 as the best possible phase noise. What I see is much better than that, and the reason is when I look well away from the crystal frequency, I don't have a 50 ohm resistor connected here. It's only the transistor, and the noise temperature of the transistor is far below room temperature. The phase noise at 50 Hertz now is at minus 139.2. And at 10 Hertz, that is here it is minus 127.6. And at 1.5 kilohertz, 141.7. And the value at 2 kilohertz may be a little uncertain, because as I programmed Linrod, there is an error at the end of the displayed spectrum, and now I am looking at tenths of a dB. So at 2 kilohertz, maybe it is a little bit higher than what I read from the spectrum here. And here is amplitude noise also, and it's clear that up to about 1 kilohertz the amplitude noise is a little stronger than the phase noise, and the difference is at maximum around 50 hertz, where the amplitude noise is about 5 dB above the phase noise. It's 1 dB per division here. And I don't know how to make the camera distinguish between yellow and white other than moving it like this. With 680 millivolts peak to peak at this point, that's 1.16 milliwatts into a 50 ohm load, means I have 0 dBm here. The measurement now is done at this point, where the carrier is at minus 6 dBm. At the wideband input over here, I am sending in 8 dBm, plus 8 dBm. I have connected a noiseless feedback amplifier to the 50 ohm output of the selective amplifier. It is a unit with 6 decibels of gain and a noise figure of about 2 dB. A conventional transformer feedback design. When it is loaded by 50 ohms, it will present 50 ohms on its input. At 50 hertz, the noise is now minus 136 dBc per hertz, and at 10 hertz, minus 127. And at 1.5 kilohertz, about minus 137.8 or so. The selective amplifier gives these readings in Linrod. I correct with 29.7 plus 1.5 for the interferometer and the notch due to the crystal, and arrive at these sideband noise levels. That is at the 50 ohm output, means I have those resistors connected. So the carrier level is minus 6 dBm. So I can convert from dBc per hertz to dBm per hertz. And I get these values. Note that this is below room temperature, because what the receiver measures is the excess noise, the noise above room temperature, and the noise is actually a bit below. Now, after adding this 6 dB gain, I measure these values and correct them, and then I find out the dBm per hertz at the input of the amplifier. That's the 50 ohm output, so I have to correct with 6 decibels. And as it turns out, at 10 hertz, I get very nearly the same result. The amplifier doesn't degrade. At 50 hertz, I see a degradation by 3 decibels. And at 1.5 kilohertz, I see a degradation by about 5 dB. Now, the result here, minus 175 dBm per Hertz, that happens to be the expected noise level of an amplifier with 2 decibels noise figure at this power level. So it is as expected, and it shows that this amplifier, I cannot add it after this resistive link that gives me the 50 ohm impedance that the amplifier wants. So I would have to add it at the high impedance output where the signal level is 6 decibels higher. I have moved the noiseless feedback amplifier from this point where it had a 50 ohm input to this point where the input impedance is very high. I also put a 3 dB attenuator on the output of the amplifier to make the output impedance nearer 50 ohms. Because of the noiseless feedback, the input impedance is reflected to the output and vice versa. The load is 50 ohms, that's my interferometer and the following receive system. But I don't need that much gain, so the 3 dB attenuator doesn't do any harm. The noise at 50 Hertz, the spur is here, and it is at minus 135 dBc per Hertz, while 10 Hertz, I have to use this tool, is up here, minus 125, and 1.5 kilohertz is at minus 140. In red I have marked the dBc per Hertz of the selective amplifier itself, measured at the 50 ohm output. It would be the same if I measure at the high impedance output with an amplifier that would be noise-free and have an input impedance of 50 ohms. When I connect the 2 dB noise figure amplifier, it doesn't degrade the close range noise much, only 0.6 dB from here to here. At 50 Hertz, the difference is much larger, and at 1.5 kilohertz, the noise is determined entirely by the noise figure of the amplifier, because the signal level is so low. If I put the selective amplifier on the high impedance output where the signal is 6 decibels higher, then the close range noise is degraded from 158.8 to 156.2. That's nearly 3 decibels. And at 50 Hertz, there is also a significant loss in performance. But at 1.5 kilohertz, it doesn't degrade much. So this amplifier with transformer coupled noiseless feedback, it introduces flicker noise, but since it operates at a higher power level, it doesn't introduce so much wideband noise. But neither of these positions is close to ideal. I need something more suitable to use the performance that I see here better. I could use the second and the third stages like the ones I used in nerds74 with the JFET design. This has the required performance, but it uses 20 transistors in parallel. I will try a bipolar instead to see whether it could do the job. This is the performance of the unit now. From the selective input to the high impedance output, which is properly loaded by this network analyzer. The loaded Q is 1.19 million and the loss 7.6 dB. So with 8 dBm input, the output is close to 0 dBm. Maybe the input is a little bit higher than 8 dBm. I don't care about the decimals here. And I can press the bandwidth knob once more, and this time it says 1.19. I will continue with this unit in the next video, where I will do experiments with bipolars for the second stage and possibly finalize the box with something bipolar, or perhaps with the junction FETs that I know would do the job properly.